Everyone, I am Souraja Kundu from an undergraduate student at Indian Institute of Technology, Guwahati, India, and I did this project, Emotion Guided Image to Music Generation, when I visited Samsung R&D Institute, Noida. So main problem statement is that we have to generate background music of photo slides, and that music should be emotionally similar to the image which we are observing. That is, it should provoke the same emotion. And to maintain this emotional correlation, we have to take a look into the psychological concepts of what is a valence, arousal. In psychology, we can define emotion quantitatively as the terms that valence and arousal. Valence means how much positive or negative emotion it is. For example, sadness will be a negative valence and happiness will be a positive valence. On the other hand, the arousal term means the intensity of the emotion. That is, we can see in this image that the child is crying very uh, eagerly. So it can be told that it is a high arousal state, and on the other hand, if it's a calm, mild emotional expression, then it can be called a low arousal state. Now, according to the levels of valence and arousal, there can be different quantitative estimates. For example, we can define the level of valence from a scale of 1 to 9, as well as the arousal in a scale of 1 to 9, defining the different levels of emotion. And there is no one-to-one mapping between this emotional correlation of image and music. So we have to train a model which will be able to predict at least a few emotionally relevant music for an image. And if we train this model perfectly to generate emotionally similar music from images, then we can use it for various applications, such as we can generate ringtones, and we can also create some sample musics of certain emotional categories, so that a music learner who is learning to play some instrument learns from this music. And also, this image to music generation can be used in guided imagery and music therapy. So with these applications in mind, we propose our model for image to music generation. First, we did a literature review. There are two main categories of image to music generation models. One is the generative adversarial network based conditional music generation models. And this example contains MIDINet, MuseGAN, WaveGAN. And for all these GAN models, we have a concerning problem of mode collapse. That is, we cannot control the image to music generation. Both are two different modalities, and for music we have to use spectrograms. And generally, when we try to use those GANs for image to image translation in this image to spectrogram translation, then there was significant problem due to this mode collapse problem of GAN. And another approach in literature for image to music generation is autoencoder transformer based sequential music generation model. So in this category of work, there are music transformer and chat musician. And we also proposed our model in this category. That is, we used transformers to generate the music sequentially. And in our case, we generated music in the form of MIDI. MIDI is a type of music format or encoding format which can be considered as a language, so that we can consider this model as an image to sequence model. And one important advantage of this image to music translation model based on transformer is that we can generate longer duration music. And we know that transformers are good at capturing global contexts, so it will be contextually relevant music as well. So first, we prepared the dataset by connecting some emotionally paired music and image data, and this is supervised learning. So we first collected some VA leveled MIDI music dataset, which was of a size of 3000. And then we also collected some images which had emotions tagged in it. For example, happy, sad, calm, these kind of tags were there with the images, and we had a dictionary which maps the emotions with the VA values. So with that mapping, we assign some VA value to the music, to the images, and finally we could correlate the image and music according to the VA values using the similarity score as given below. So for each image, we paired it with one music, and thus we created a set of 3000 image music emotionally paired dataset. The model workflow is as follows. First, the image features are extracted using some feature encoder of some variational autoencoder, or we can use a beta variational autoencoder or adversarial latent autoencoder, or simple models like VGG or InceptionNet. So after this image features are extracted, we will parallelly extract MIDI features. And for that MIDI features, we have to use some sequence to sequence model. And after this, both the features are extracted from image and music, we concatenated the features. And this created a complex multimodal representation of both the image and music of the same emotional category. And after that, we used a MIDI decoder, which will give this probability vector. And these are the class probabilities of different MIDI tokens. And with this, we will use some argmax to get the most probable MIDI string and append it to the generated MIDI string to create the whole MIDI sequence. And this is the overall workflow of the model which we proposed. And for the different components, we look at this slide. That first, we extracted the image features using this VGG16. So one reason we use the simple pre-trained image encoder is because VGG16 is already trained with a very huge amount of ImageNet dataset. So it will be already efficient at extracting the relevant features from the images. And on the other hand, for extracting the music features, I used 3 levels of transformer encoders. The earlier models have never used the transformer, so this is one of our proposed changes in the music feature extraction model. And after this, transformer encoders have created the music representation. I concatenated both of them and then passed it to the MIDI decoder. The MIDI decoder contains some transformer decoders followed by dense layers, and we stacked 3 of these transformer decoder and dense layers stack to create the final probability vectors of all the MIDI tokens. And this is how we will predict each MIDI token, which will be concatenated or appended with the final MIDI sequence, which will be generated. And that MIDI sequence, which is generated, will be emotionally correlevant to the both image and the music. But the loss function of this supervised training, first of all, since this is a multi-class classification problem, we use this categorical cross entropy loss function. And also, we used a valence arousal loss function. This valence arousal loss is proposed by us, and which tries to maintain the emotional relevance of the proposed music. So for to calculate the valence arousal loss, first we have to predict the MIDI token sequence using this system of taking the argmax and predicting the probability of tokens from the vocabulary. We will create the MIDI token sequence for both the true and predicted MIDI. And after this, we will convert that to a MIDI string because we have a dictionary which maps the MIDI tokens with the MIDI strings, and thus we append and create the true and predicted MIDI. And then we parallelly trained a music valence arousal predictor model, which is nothing but a 3-layer fully connected layers, which was trained with paired music data with their corresponding valence arousal levels, so that we can use this pre-trained music VA predictor to predict the VA values of both this true and predicted MIDI token sequences. And once we have the VA values of this true and predicted MIDI, we can calculate their L1 norm which will be the valence arousal loss value. So we trained our model using these two loss functions, and these are the quantitative results. We have tried different models to verify our performance. So to compare our model with the baseline, our baseline was a LSTM encoder 2 model. That is, in this MIDI encoder, we used 3 transformers. So the baseline model had only 2 LSTM blocks, and there was no transformer in the decoder or no LSTM in the decoder. The decoder was simply, after concatenation of this music and image features, it was just some dense layers followed by this prediction from argmax operation. So this was our base model, which we name as LSTM encoder 2. And we also verified our model with the other variations of this transformer based image to sequence model. For example, the trans-enc 3D3 means there were 3 transformers in the encoder, 3 transformers in the decoder, and we used VGG as the image feature extractor. Similarly, we tried using inception as the image feature extractor. Then we tried using 4 transformers in the encoder and no transformers in the decoder. And also we tried 2 transformers in the encoder and 2 transformers in the decoder. These were all the models used for ablation experiment. And for validation of our proposed VA loss function, or the valence arousal loss function, we compared our model with the model without the VA loss function. And we can see that in terms of these 4 evaluation metrics, our model has outperformed all of them. So the 4 evaluation metrics are music quality loss, polyphony rate, pitch entropy, and groove consistency. And we can say that the pitch entropy is how much variations is there in the music. The more variations are there in the music, the more enchanting it will be to listen to. And similarly, we can denote the other qualities of the perceptual relevance of a music using all the 3 metrics. And the music quality loss is an aggregated version of how much quality loss is there in the music. So the lower the losses, the better the generated music will be. And from this qualitative results, we can see that our model outperformed the baseline model and also all its ablated versions. This is the loss convergence visualization. We compared our model with the LSTM baseline model, and we can see that our model's loss function converges much faster and to a much lower value. So this also mathematically verified the relevance or the importance of a model. So next I want to play some generated music. So these musics were generated after only 15 epochs of training and on a small dataset of 3000 image music pairs. And first, this is the image we fed to the model. This image is not belonging to the training dataset. This is an unknown image. And from visualization, we can see that the image expresses some happiness, some enjoyment, and there is also this violin players which are creating a symphony. So first, I'll play the proposed model without the VA loss function.
Think we cannot listen to it.
Can I do something to share the audio as well? Yeah. Is there any option to share the audio? Yeah. Hmm. Is it audible? Yeah.
Not audible.
Mm, okay, it's embedded in the slides. So will it be possible to share the slides and listen to the musics? Okay. And maybe I can share the slides to listen to the music. And finally, the conclusion is that we generated the music quality, which was of a better quality and of a longer duration. And it had emotional alignment by using the novel Valence-Rosa loss function that we proposed. And our model performs well even when it is trained on a very small data set on a smaller number of box. That means that it is not overfitting, as well as there is a good generalization capability. And also, we can say that this model is very simple to understand. There is only one image feature extractor, one music feature extractor we are concatenating, and then there is a music decoder to generate music. So it's a very simple model to understand, not very complex. And this model is efficient and can have multiple potential applications. As I discussed, that we can generate ringtones, we can create some example musics for music learners, etc. And the future work is that we can incorporate multi-instrumental music in the dataset. For now, this the music generated is of piano music, but we can augment the dataset to make it suitable for multi-instrumental image to music generation as well. So this is what my references are, and thank you for the presentation, and I will be happy to answer any question.
Okay, thank you very much for your presentation. Any questions from the audience?
Hello, I have a question.
Okay, please go ahead.
Thank you. Firstly, thank you very much for your presentation. I think it's very good. And actually, I have a question about the quantitative analysis. Could you go to that page? Yep. For the baseline, I saw you used encoding 2. Maybe I missed something, and not very sure about the difference between encoding 2 and 3. But since you are using LSTM and transformer, which are different, and also the encoding's different, I was wondering why there's no comparison between LSTM and transformer using the same encoding network.
Okay, so first of all, this encoder 2 means that in the encoder there were 2 LSTMs, and for our model transcend 3 means there were 3 transformers. We also tried our model, like experimented our model with 2 transformers in the encoder, and it was also performing well. I have not put these results here, but this transformer encoder to decoder 2, we can consider that this has 2 more transformers in the decoder. We also tried our model to like remove the 2 transformer decoders, and with only trans enc2 and LSTM enc2, and it was definitely performing much well. And I actually presented the results here, which gave much significant improvements. And yes, of course, LSTM was not performing well in this case compared to all the transformer models.
I see, understood. So you mean
Hmm.
like adding transformer decoder would actually improve the result
Yes, yes,
compared
that is,
to only using 2 transformer encoder, right? So you only put this result here.
yes, I wanted to show this
Understood.
here. For example, this
Okay.
trans 4 is just 4 transformers in the encoder, and it did not have any transformer or any LSTM in the decoder, and it still performed much better. So all the
Um,
transformer variants are performing much better than any kind of LSTM variants. It is because the transformer has a more contextual feature extraction capability.
I see, I see. Thank you very much for the explanation.
Thank you for the question.
Okay, any other questions from the audience? Okay, I may ask some simple questions. It was not clear for me. Why did you use LSTM as a base model?
Okay, so this was from a previous paper.
Okay.
Okay. So this paper in Mendes and Arbandara, show and listen. They proposed this baseline model that they used two LSTM encoders,
Mhm.
and there was no decoder. So I improved from that model.
Okay, that you start this research based on that paper. So
Yeah,
that time you say it's as a base model.
yeah,
So I think in that case it's better to say that it is as a kind of the previous work of this research direction. Okay,
mhm. Okay,
not as a base model.
okay,
So I think because it's going to be a little, I don't know, I don't know. I was confused because there was completely someone made the base model. I don't know. We cannot say it is exactly as a base model, no, sometimes. Okay.
okay, sure.
Okay. And any other questions? If so, no questions. So I'm going to, okay. Thank you very much for your interesting presentation. Best luck with your future works. Okay. Thank you.
Thank you.